So let's talk about LoRa a bit before using the function. Yeah, before continue the pre-training process, let's see how the model performs for the given prompt. So here I have just given the prompt. So it is same thing as we have done. So in the earlier experiment we used GPT-2. So at the end of the experiment, we just demonstrated how the model generates or completes the given prompt for various checkpoints. So we repeat the same code. There is no change at all. So the same, just change the prompt, of course. Then the remaining set of statements remain same. So if you execute this, you can see that it is able to generate a coherent test, and also it's meaningful, right? So if you read this, I hope Feynman famously said this, and if you execute this again, you will end up with a different sentence, but at least it is able to complete the sentence and it retains the world knowledge. That's a very important thing. And what happens if I give a prompt in Tamil, right? So I have given a prompt to the same model in Tamil, and of course I executed this cell some 3 to 4 times, and then I have seen that the model is, though it generates the text in Tamil, but it is not coherent and it is not some sort of meaningful, right? So it's sort of it generating a random words in Tamil. So I executed some 3 to 4 times, maybe after some 10 to 20 attempts, it might have generated different sentence. But let's say that the model is unable to generate a coherent text in other languages, especially in Tamil, because the model was trained on, maybe the model just has seen a few examples while it was pre-trained on 9 trillion tokens. So what we are going to do is we are going to give them more examples of how the Tamil language looks like and how all those steps. So let's do that. Okay. So what is LoRa? That is the first question. So how it achieves. So we have 1 billion parameters. So instead of updating the weights of 1 billion parameters directly, what LoRa does is, remember that the entire model, decoder model, contains weight matrices that takes a lot of weights, especially the weights in the multi-layer perceptron layer, right? So what LoRa does is, it is a simple kind of SVD stuff. So it decomposes the weight matrix into weight matrix W into low rank matrices, like we decompose a matrix in SVD, right? It's the same singular value decomposition. So you can see that the input is X here with a dimension D. So LoRa adds an adapter for each weights. Of course, we can customize it, whether we need to add adapters to the linear weights in the entire network or to the attention heads, only to the projection layers in the attention heads. So we can control all this. Just for the sake of understanding, let's say we have just a single weight W, and then we decompose the weight into two matrices A and B with rank R. Okay, and A is initialized randomly. The matrix A is initialized randomly. Typically, it is from Gaussian, and B is initialized to 0. And during the forward pass, right? So what really happens is we pass X through both the layers. So we freeze these pre-trained weights. Let's say we have pre-trained weights from Llama 3.2. So we freeze all the pre-trained weights, meaning that the gradient won't be computed for these weights. But during the forward pass, we make use of these weights and pass X through this W, compute WX. Also, we pass the X through this low rank approximation matrix. We compute something called as delta WX. Okay, so and then we add these representations, because both of them will return representation of having same dimension. And then we add this and we take this, we repeat this process for all the layers. Okay, that's how LoRa works. But LoRa works in the forward pass. But during the backward pass, what really happens is we really don't compute the gradients for W, right? So instead we compute the gradients only for A and B, because we have set the rank to very low, right? So typically the value for the rank is much lower than the embedding dimension. So say for example, in this case, embedding dimension is 2048, but we can set the rank at 16. So 16 is much less than 2048. So the number of parameters is reduced drastically. And of course, what happens to the performance and what happens to the world knowledge that the model has gained by looking at all 9 trillion tokens? It seems that it gets affected, but not much. It doesn't hurt the performance of the model much. So of course, anyhow, if we really don't have much compute, it is a best way to continue the pre-training or fine-tuning the model. So as I mentioned earlier, these are all the points. Remember, during the forward pass, we compute the representation. The W is pre-trained weight, which we freeze during the forward pass, and del W is, again, it is a approximation matrix, which we can decompose this into two matrix B and A with appropriate dimensions. Okay, so all these things. So while we configure the model, or when we add the adapters, LoRa adapters to the model, we need to configure the LoRa. So we need to set some parameters, like especially the rank is the key parameter. We have to set, of course, increasing the rank always helpful because it gives you the better approximation, but it also takes a lot of computation. And there is another parameter called alpha, so which in fact does the scaling operation. So we have to set the alpha as well. You can read more about LoRa and how actually the approximation works, all these stuffs from the paper. It is it is well written, so you can understand most of the concepts without much difficulty. So the key takeaway is A is initialized randomly, B is, of course, we have multiple choices, but let's say we initialize it with Gaussian distribution and B is initialized to 0. We have to set what the value, the rank value, and also we have to set the alpha value. Okay, so that's what we need to set. So again, we use the module from Hugging Face, which is PEFT, and we import this LoRa config and also the task type, because the task type here implies that we can fine tune the model for multiple tasks. Here we are doing continual pre-training, so the task is task LLM, but we can do token classification or sequence to sequence stuff, right? Or whatever. There are about some 6 to 7 types of tasks, but here we are using the causal LM, so we just set task type also. And we are setting inference modes equal to false because often, PEFT is used during the training, but of course you can use it in the inference as well. And we are setting the rank to 16. Okay, so that's the default value. So you can go from all the way from, 1, 8, 16, 32 multiples of 2, right? But 128. But increasing the rank size, remember that increases the memory requirement as well. And also, since we have a decoder model, we have multiple weights at the multiple layers, right? One is in the attention layer where we have WQ, WK, WV, and also WO. And in the feed forward network layer, we have the Ws. So we can say where we need to add these LoRa adapters by passing the layer names to the target modules. Okay, so here we are just, again, for the sake of demonstration, we are just going with adding adapters to WQ and WV. But if we really want to add adapters to all the layers, okay, that makes sense. But you can do that very easily by setting, by passing these names. These names, Hugging Face, so if I'm not wrong, follows sort of same template for all the models, especially PEFT supports some 6 to 7 types of models. So they have all the common names like Q project, K project, all these things. Of course, you can print the model and look at the names associated to each module, each PyTorch module, and pass it to these target modules. Okay. And now we have to really check. The model has 1.23 billion parameters, but after adding these adapters to each layers, then we have to count the number of trainable parameters because we freeze the rest of the parameters. We just need to train the the parameters in the adapter layer. So we have to count that. So if we can count that manually. Also, we can use the inbuilt function LoRa model. Remember, first I have to add these adapters. So you can add them in a very fine-grained way, but the better approach is to use this function get PEFT model. So once you have a model and then configure the LoRa, then if you call this function get PEFT model, it will add the adapters automatically. Okay, so you can control them, but the best approach is to use the model for if your task is very common, right? So once you get the model, then you can count the number of trainable parameters. It turns out that we have only 1.7 million trainable parameters. We need to just train 1.7 million parameters, which is again just 0.13 percentage of all the number of parameters. So we have 1000 million, but instead we are just going to train 2 million. Okay. Yeah, you can print the LoRa model and then see where the adapters are actually added. Recall that we have this decoder layer, attention layer. Remember, we configured so that the adapters are added only to the attention layer, especially to the Q project and Q and query and value, right? So for Q projection layer, we added a LoRa, right? So we can see that the LoRa linear is added to the Q projection. Similarly, remember, and also look at LoRa A and LoRa B, right? So LoRa A is recall that just take a screenshot of that approximation diagram and then keep that with you. So you can see that LoRa A, the model's original input dimension is 2048 by 2048, and we have said rank horse equal to 16. Therefore, the matrix size A is right 2048 by 16, and the matrix size of B is 16 by 2048. So when you do this matrix multiplication, it matches the dimension. And there is no adapters added to this key projection matrix because we haven't said that. And we have an adapter added to V projection, right? So again, the same thing, LoRa A, LoRa B, but that only we have 16 decoder layers. So in all the 16 decoder layers, we add uh, these adapters to Q project and then reproject. We leave the remaining axis. That's why we need to train only 2 million parameters. So if we add adapters to, let's say, for all the MLP layers, all the linear layers, then we may need to train more number of parameters, maybe say, for example, close to 100 million parameters. Okay. Yeah, so as I mentioned, it's only updated to projection layers. Yeah, so as I mentioned earlier, that we actually freeze the parameters, right? So let's manually verify that whether we have freeze the parameter, meaning that for some of the for most of the parameters in the model, the required grade attribute should be false. So let's check that quickly. Let's calculate the number of parameters. It's 123, I mean 1.23. Now we check the trainable parameters and we just check that the model has a lot of parameters like linear, all those stuffs. Then we check whether the parameters requires gradient. So if it requires gradient, then increase the number of parameters. And if we do that, we end up with the same number, 1.7 million. So the model parameters are freezed, right? So it is always good to manually verify as much as possible. Even though we rely on HF, whenever possible, it is good to manually verify whether things are going the way we want. Okay. Okay. So what does that mean? So now I need to train 1.7 million parameters. It doesn't mean that you can increase the batch size to some 100 very easily because you still need to store the model, right? The entire model parameters because we use all those parameters during the forward prop, and also when we need to store these activation values in the model, and also we need to store, do this A B multiplication and reconstruct and add the gradients to the model. Okay, so because doing all these things will not drastically reduce the number of parameters. So often the case is that we get at least 50 to 70%, not 70%, 30 to 50% of reduction in number of the memory requirement. So instead of 22 GB, we may end up using just 10 GB because 5 GB plus other stuffs like, so we need 10 GB. So if we which means we can increase the batch size because the model training takes only 10 GB of RAM. Okay, that's quite good. And let's check the configuration of the LoRa model. So because again, cross-checking steps before training is, saves money. Okay. Now the training is nothing different from GPT-2. The only change is that we converted the model to a PEFT model via LoRa. There are other adapters. Now we prefer the LoRa. So we just converted the model to LoRa model, and the entire training procedure remains same. So it is well integrated with the trainer. And for now, we are setting the batch size equal to 2 and then FP16 equal to true. Say for if your GPU supports BF16, which is most commonly used today, then you go with BF16 as well. That there is nothing wrong. Okay, and the rest of the steps we already discussed, and it remains same. No, nothing new. And we just pass this to the trainer model. Okay, sorry, trainer class, and you can see that instead of passing the model, now we are passing the LoRa model. Okay, so which means that now the trainer only trains the adapter layers, not all the parameters. And you just call this and you will, it just trains the model. And you can see that after some 14k steps, the train loss, because we set the batch size to very small, maybe 2 to 3, you can see that there is a uh, sort of big oscillations. But we just observe that if we set the batch size to 8, which is possible, per or in effect 8 per device, so that 16, the training loss becomes quite smoother. Okay, and similarly you can look at the validation loss, but number of samples in the validation set is very small, so you can see that it is decreasing smoothly. Okay, so the model used approximately just 10 GB of GPU memory. So even though we have 48 GB of memory, out of that it uses just 10 GB, which means we can increase the batch size from 1 to 16 very easily. Okay, and because we are also using FP16 or BF16, we can increase the batch size still further. Okay, and you should always remember some pitfalls of using the notebook, because notebooks are interactive. You can go back and forth between the cells. But remember that once you compute the LoRa model, because to create the LoRa model, you need to pass the model and the LoRa config. Once you pass that, the LoRa model gets created. But while the LoRa model gets created, it also modifies the model in place. Okay, because the model actually holds the original model. But when you do this, add this adapter, it also get affected reflected in the original model. Okay, so going back and executing the original model or using the model parameter as is gives you a different result. Okay, so be mindful when you are using notebook to experiment with these LoRa and quantization steps. Okay, and it makes sense why they do this in place modification, because we do not have enough memory to store two different models, right? So if we want to store LoRa model and the original model separately, then we need two 5 GB, which is 10 GB of memory just to store different models. Okay, yeah. So after training the model, we are just going to load the checkpoint and see how it works. And then we just loaded the checkpoint from after training the model for 15,000 steps. And then it makes, so I just executed the model twice. So the first time, I don't know what it has generated, but in the second time, it was able to generate at least some meaningful words. Okay, so this is the prompt, and it is able to generate these two words are meaningful, and also this is sort of coherent. Okay, just again for this is a demonstration, but we can't expect much from the model. But the procedure remains same if you continue pre-training the model on all the samples from the Sangraha dataset. Maybe after using all the samples, it might adapt better. So the immediate question is, because we fine-tuned the model or continued the pre-training the model on a different domain or a different language, so we might ask the question like whether the model retains the world knowledge after continued the pre-training, and also we haven't done the full pre-training. We just modified adapter parameters in the adapter layers. Okay, of course we have to conduct the experiments to really validate, and it is model specific. Okay, and as usual, once you train all these stuffs, you can store the PEFT model, and you can load the model back like we used auto model. Once we pre-train the model from scratch, we can store the model, and to load the model back, we used auto model um, class from Hugging Face. Here, we use the PEFT technique to train the model, and we store the model. And if you really want to use that model for inference, because this model contains an adapter layers, so if you really want to use that for inference, then you have to use uh, the class PEFT model, not the auto model. So you have to use the PEFT and then reload all the parameters, and you can use it for inference. Remember, for inference, it reduced the computation much. Yeah, this is the same question. So, but we just check that the model still retains, the world knowledge, and it is able to generate the coherence sentences that is coming from Feynman, I guess. So it is not Feynman would have said all these stuffs. Okay.